Welcome to the Astrophysics Podcast. Well, folks, it's been a year now, 12 months and 12 episodes of the podcast, 12 interviews with 12 different astrophysicists. Now that Season 2 has began, I, the number one fan, thought it might be nice for us to get to know the host of this podcast. But first, what do you see when you try to picture a theoretical physicist? This, of course, is a loaded question, but one image that might have popped in your head is of someone with disheveled hair scrawling mathematical calculations on a giant chalkboard. Nowadays, some scientists still do that, but most of us do our calculations on giant supercomputers instead of a giant chalkboard. But we still usually have the disheveled hair. Here's an example of how this works. Imagine you have a planet orbiting a star, and you want to know where it will be in the future. This can be calculated using pen and paper, and scientists like Johannes Kepler and Isaac Newton wrote down the equations to solve those problems centuries ago. But what if instead you have a whole solar system of planets, all interacting with each other, and you want to know what that system will look like in a few billion years? That becomes a lot harder, if not impossible, to do by hand. So instead, we take all of those equations describing these interactions and turn them into an algorithm. A series of instructions that will tell us if we know where the planets are now, where they will be in a short time later. Then you repeat those instructions over and over until you evolve the system for billions of years. This type of repetition is the sort of thing computers are perfect for. The field of computational astrophysics is tremendous. Computational algorithms are used to solve so many problems that it is often considered its own separate branch of study. Some say there are theorists, there are observers, and then there are computational modelers. We sometimes call these computational algorithms simulations. The idea being, you set up the initial scenario and see how it plays out on the computer. It's very powerful for learning how astrophysical systems works, since we usually aren't close enough to these systems to see what's happening in detail, and we certainly don't have the time to sit around and watch them for a billion years to see how they evolve. Our guest today is normally the host of the Astrophysics Podcast, but now it's my turn to interview him. Paul Duffell is a computational astrophysicist who writes computer code to evolve the equations of astrophysical gas dynamics. His codes have been used by researchers around the world studying many different types of astrophysical systems, including black holes, supernovae, planets, gamma ray bursts, tidal disruption events, and more. We'll be talking with Dr. Duffell about just what it takes to put the universe on a computer. I'm Abigail Polin, and this is the Astrophysics Podcast. All right.
How are you feeling?
Nervous.
It's going to be fine.
I think it'll be. I mean, we're pretty good at talking to each other. I hope.
We're okay.
All right. Should we get started?
Sure.
Welcome to the Astrophysics Podcast. No, that's not what I'm doing right now.
No. You do it.
I actually do this talking to you now. All right.
Yeah.
Welcome to the Astrophysics Podcast. I'm Abigail Polin, and today my guest is Dr. Paul Duffell, Professor of Physics and Astronomy at Purdue University. Dr. Duffell, thank you for joining me.
I'm happy to be here. Where else could I possibly be?
Good question. Many of you probably recognize Dr. Duffell, or as I'm going to start calling you, Paul, as the host of the Astrophysics Podcast. So should we explain what's going on here?
What is happening?
Yeah.
Sure. Well, okay. Which aspect should I explain? The fact that obviously you're interviewing me now for some reason. So now it's your show.
Well, yes, it's my show. I thought it would be nice, this is the 1-year anniversary of the Astrophysics Podcast, to meet your host a little bit.
Sure, maybe that's nice. We'll find out. Should we also explain how we know each other?
Possibly. The first sample question you have for me here is, how did we meet?
Okay. Well, anyway, so you should mention, because you were the first guest on the very first episode of the Astrophysics podcast 1 year ago. And and we didn't actually, it's kind of silly. Actually, people who know us think it's kind of silly because I nowhere during that time, in fact, I kind of am lying through the whole episode.
Yeah, so you're pretending you don't know anything about my life or upbringing or where I'm from, but in reality, we're married, yes.
Yeah. So, and the reason I do that, it's not like I'm trying to hide that we're married. It's public knowledge, but
I should hope.
But it was just the first episode, and I wanted to be able to do a first episode with, first of all, someone who's a professional in the field that's doing this, but also somebody that I could practice on. So we did a whole episode that was just a first take that didn't air or anything.
Yeah.
Where,
playing with audio equipment and getting used to how to do this.
And we had to fix a bunch of things. So that was the main reason I interviewed my wife, but I couldn't start it by saying my first guest is my wife. Like that would have been like a little bit. That would have sounded like, I don't know.
I don't know that you would have gotten the listeners. Yeah,
different kind of podcast. Anyway, but that's okay. But anyway, so I was a little bit cagey about. I didn't actually like explicitly say we were married. In fact, I even pretended not to know like where you were from. It's like say you grew up on a farm, and I've been to that farm.
Yes. So we got married on that farm.
So like, it was a little disingenuous, but that's okay. Now we'll have the proper version, but except you're the host this time.
Yes, I'm the host. Shall we get started?
That sounds great.
All right. So, Paul, where did you grow up?
I grew up in a city called Seattle, Washington.
Oh, a small town?
No, it was not a small town. It was a small city, I guess. I mean, it's a big. I don't know. It depends on where you're from, whether you consider that a big city or small city. But it's like, I think when I was a kid, it was like somewhere like around the 10th-ish biggest city in the country. But anyway, Seattle. Everybody knows Seattle if you're from the U.S. But it was kind of nice. I'm really glad for my opportunity to have grown up in a big city, or a city where there was lots of just a lot of diversity, a lot of different people you meet everywhere, like that. You just see all kinds of new things every day, and so that's a lot of fun.
Yep. Yeah, we've compared a little bit of our childhoods, the difference in things like walkability, that kind of thing.
Right, yes. The ability to just walk to a coffee shop or that sort of thing is quite nice.
And if you haven't been there, it's one of the most beautiful cities in the U.S. I highly recommend it.
I know. I didn't appreciate it growing up. In fact, as a kid, like I hated hiking and stuff like that. It was like one of those annoying things your parents would always drag you to, but they'd always drag me to things like that because it was so much of it. Like there was so much beautiful nature all around us, and I appreciated none of it because I was annoyed that I had to walk.
I think that might be universal to childhood, right?
Yeah, it's like, But
we don't appreciate what we have.
Yeah.
All right. So, do you have any memories of the first time you realized you were interested in science? Were you interested in this as a kid?
This is great, actually. Every single one of these questions I've asked now 12 times to 12 different people, and so I've thought about my answers.
So you're more prepared than we were.
I am. That's why I'm thinking about it, and I've thought about this a lot, is, the thing I remember really distinctly when I was a kid, my dad had this big book that was it was like he got it from National Geographic or something like that, and it was this big kind of coffee table book, but it was like about the solar system, and each page was like a different planet, and
were they like spectacular pictures? Or?
Actually, so there were some nice pictures, but a lot of it was just sort of like cartoon drawings.
Nice.
And so like they were like take cross sections out of the Earth and just like take it away, and I was like, whoa, there's all this stuff inside, like the core. What's that? Like what? Like just like I'm just enraptured with this idea, and that each one was a different planet and all different kinds of things about each planet, and that just kind of like got me really excited about like space and just like all the things that you could like the idea, like before that I didn't think of planets as something that like you could dissect and understand the interior of. I just thought of them as, well, there are these things that are there.
Yep.
So I don't know. That to me was like, I guess if you're asking about a first memory, that's like when I like really that kind of is, I feel like, is core. Like I remember really distinctly flipping through that book, and I kind of felt like I wasn't supposed to. Like I wasn't told about this book. It was just one that my dad had gotten and like not mentioned it, but like I found it and I was like, it's his book. I'm sure he was like really excited that I wanted to look through it, but like I thought it was like the grown-up book that I was looking through.
So that tends to cover your next question you often ask too. Yes. is were your parents interested in science related fields? Yeah,
they were. I will say, okay, so my dad, my mom is my dad is a Catholic deacon, and my mom is she was the director of a Seattle-based nonprofit called Committee for Children, which develops curricula for schools to teach conflict resolution skills to children. And so they actually, they had very different paths from me, but I picked up different things from each of them. Like my dad is always like fascinated by science and especially astronomy. And he would whenever we would go out camping, he would bring the binoculars and he'd go like, "That's Deneb, that's the summer triangle," like, and explaining all this stuff to me, what all the different names of the stars were. And
can you point out any constellations now?
I could give you the summer triangle. That was not too hard. And everyone knows Orion and things like that. Cassiopeia.
It's better than, that's very typical for astronomers. That's why I asked.
Oh, yeah. Yeah, it's actually, that's right. I'm not an expert on constellations by any means.
It's kind of an in-joke that, we know less about the sky looking up at it than the average Girl Scout.
That's right. I remember there was some meeting we were at, and, there was a whole bunch of astronomers at this big meeting, and we were outside late at night, and there was some bright thing in the sky, and everyone was just arguing about, is that Jupiter? No, I don't think that's Jupiter. Like, they're just kind of like, everyone just exactly like if you got 50 random people, they would have the same argument about whether that was like a planet or a star or something.
It's twinkling. No, it's not twinkling.
We don't have a lot of the like knowledge of our immediate surroundings that we have, like that we see in the night sky as much as people might think we would. But anyway, so that was my dad. He was very deeply interested in that stuff. My mom was, really, she wasn't as much science, like I wouldn't, she's very interested in evidence-based methods and things like that, but not as much in like, academic science specifically. But what I feel like I got from her was like, and she wouldn't have expected this when I was a little kid, but like her abilities with people and
Absolutely.
Organization and getting people together and knowing how to make the most of your team and that sort of thing. I feel like that's what I've really gotten from her. And it's funny, as like when I was a teenager, I don't think that they would have expected that of me so much. They would have expected me as kind of a spacey kid that like just did science on my own. But every year, my mom for Christmas, or actually for like first day of school maybe, would get me a planner, and I would promptly just toss it in the corner because I couldn't use them, right? But because she just thought he needs some ability to organize his life if he could get a planner, and I was like, this is never going to be used. So like it didn't seem like I would take after her, but now sort of growing up, I've gotten a lot of that. I feel like I've gotten a lot of that from her. Yep.
And we can circle back towards the end when I ask you about your current job,
okay,
how that plays into your daily life today. Okay. I'm going to ask a question off script here because I think it's interesting because I know you. So you've been interested in science from a very young age. You said you've had parents exposing you to it. So did you always know that you wanted to be a scientist? Has this been a very direct path for you?
That's a good question. I didn't really know. I didn't really understand that this was an option exactly. I knew I loved, so when I was in like high school and stuff, I knew I loved math. When I was in middle school, I knew I was good at math, but in high school, I learned I actually liked it. But I really didn't think that science would be something that I would do, or I just didn't think of it as a job. I was like imagining I would work for some company, doing math first. But I didn't, when you're a kid, when you're a teenager, jobs are very abstract, right? You go like, well, you'll learn math and then you'll get a job. And it's not, you don't really think about, the details of what that would entail. Yep. So yeah, I didn't really have a clear picture of that, that I was going to do science. I knew that I liked, my dad would turn me on to science books like Stephen Hawking's Brief History of Time and things like that, and I would get into that stuff, but I didn't think of that as a job that you could do.
I mean, valid.
It still doesn't really feel like a job.
Yeah. Sometimes I'm still surprised it's a job. Okay, so you liked math and science in middle school and high school. You went on to college, presumably?
Yes, and I think at that point, I knew, by the time I went to college, I knew I liked physics specifically. And then then I started to have an idea, like there were people that did this, that did physics. But I did also, even at college, I didn't really know what I was doing. Like most people in college, I didn't really know. I was just kind of like, well, I'll learn this, especially at the time. But I think even now we still have this picture in our heads of you go to college and then when you get out, you get assigned a job. Yes. Right? But
you got to go to more school or you go.
But that's not how it really works. You get out of college and then suddenly, there's not like people clamoring to give you a job, right? I don't care how well you did on your tests and exams and homeworks and stuff. It takes time to get that. And so I was for a while just working at coffee shops and record stores and things like that. I didn't know how to get from there to a job that actually used the skill set that I had.
So what changed then? So presumably at some point, I'm going to stop saying presumably. We've covered. You're my husband. I know what happened. So how did you transition then from that gap time, which is not actually that typical for us? A lot of people go directly from college to grad school, whether they should or not.
Right. Right. That's the standard thing. And it's almost always recommended that you go straight from college to grad school because you have a better chance of getting into grad school if you go right out of college.
But maybe not the better perspective once you get there.
But yeah, whether you do as well, you might do better afterwards if you have some time in between. But which I did. I definitely was valuable to have that. But yeah, I was just working at record stores and things, and first of all, I had started to have respect for this idea that people don't just pay you to just be good at math, right? You have to be providing some sort of service to somebody. And so, when it's, when working a lot of different jobs, I would, get more perspective of that. Like we were paying you because you were doing something of value. But yeah, I was doing a lot of just working random jobs, but then I had this idea, that eventually I wanted to go back to grad school. I thought about it a lot, and I realized what I really liked was science. I was interested in, I remembered I had seen things on Nova specials and things about black holes and stuff. And I even wrote, in high school, I wrote a report on black holes. But in all of college, even though I was a physics major, we never took a course that taught me what a black hole was.
Yeah, unfortunately, it takes quite a bit of physics before we can understand those questions.
And it's really hard. And so I realized, you know what? I have a physics degree. I should be able to learn this stuff. So I took some time, and I thought, okay, well, I want to go to grad school, but I, need, it had been 3-4 years or something. Can't remember how long. But then, so I decided I'm gonna learn this stuff again, or get a refresher on this stuff. And so One of the things I did was I just got my old textbooks and just tried to do, a lot of the problems. But then I was in Seattle still. I went to college at the University of Washington, but and so I had gone there. But then I went back and I just showed up to grad courses, and I walked in the room. At first, I would tell the professor, I would say, hey, I'm sitting in on this, I'm not registered or anything. I just am interested in sitting on this course. And I should say, anyone who does this, they, occasionally get a professor who will be like, oh, I don't know if you're not supposed to do that. But the vast majority of professors will be like, oh my God, that's so cool. Yeah. You want to just show up to my course and just sit in on it?
So long as you're genuinely there to learn. Yeah.
And so I was just getting education for free. No, I wasn't getting any, credits for it. That's the thing that you're really paying for. But I was, and I took graduate courses on, electromagnetism and quantum field theory and just a bunch of different courses. And I got some textbooks and I read about general relativity and things like that. And I just, worked hard, and I was like, my goal was I was going to go to grad school, and I applied to a bunch of grad schools. I got rejected from all of them. Well, because I hadn't really had the research experience. I hadn't really done anything. I had no letters of recommendation realistically. I had professors I'd sat in on their courses, but that's it, Right. And so I took a lot of time, and I did I think a couple years in Seattle doing this, maybe 1 year in Seattle doing that. And then I decided, a couple of the places I applied to, I applied to NYU and Columbia. And I thought, I'm just going to move to New York, and I'm going to do the same thing at Columbia. And so I moved to New York City, and I took classes from Columbia too. So I had done that at University of Washington, then I did at Columbia. I took courses on all these different subjects, and it showed up. And I continued applying, but I also got to working with a professor, Amber Miller, who was a professor at Columbia at the time. She was an assistant professor then. Now she's, I don't know where she is. She was at, the dean at UCLA, but I think she's moved on to another job since then.
USC maybe?
Maybe it was USC. Anyway, the point is, it doesn't matter. But this was back when Amber Miller was just a newly anointed assistant professor, and I got to working in her lab. I just cold emailed her and was like, hey, I would like to do research. And just out of nowhere, and she's like, okay, sure. And so she put me on some research projects, and I learned. By then I had managed to get a few different letters of recommendation together. I sat in a course by Brian Greene. I got a letter of recommendation from him. I applied to grad schools again, and I didn't get into any of them. And I just stayed in New York for another year, and I kept doing this. I don't remember exactly how many times I applied to grad school, but it took at least 3 tries. Okay. Until I finally got into NYU.
All right, so third time's the charm.
Probably.
You got into NYU.
It might have been the 4th time that was the charm. I'm not sure. I can't remember, but
so you finally got a yes. You started grad school.
That's right.
At NYU.
That's right.
Which is coincidentally where we met.
Yes.
Where along this process do you think you kind of started to actually understand what it meant to be a scientist, like what we actually do?
I didn't really have respect for that until I was actually in grad school at NYU. I was doing research at Columbia with Amber Miller's lab, but I didn't really understand what it meant, like what it means, like how do you be a scientist? Like I knew how to be told okay, you should figure out this problem, you should, I was doing we were in a lab designing telescope filters, and I was figuring out how to test them and that sort of thing, but a lot of that was doing things that there was a clear path forward for. It wasn't about when you really are a scientist, it's more about figuring out what project to work on. What is something? How did you figure out that it was a good idea to test out fabricate telescope filters and test them out, and that you had the facilities to do this? So that's the part where I think I really learned in grad school is how to be a scientist. How do you come up with what it is you're working on that day? So.
And do you have a philosophy of what that means for you?
Yeah, I would say for me, I mean, I don't know. I don't know how to summarize it. I think a lot of my guests, in fact, that's the question I should say that every single guest answered almost all. It's the same answer. Either they said they still don't know how to be a scientist, or but the vast majority of them have said they learned it in grad school. And that's basically what grad school is teaching you. It's teaching you, and they probably gave more eloquent answers than I will, but they basically, so you can listen to other episodes, they'll be better. But basically the idea is, when you're a student, or even if you're working in a lab, there's a period of time where you're being assigned a task, and then you do the thing, and then you hand it back to your advisor, and then they figure it out. But at a certain point, you learn why that task, how they came up with how to come up with a task to do. How do you decide, like, oh, I'm going to try doing this now, like, right. We've been doing this. Maybe if we did it this way, we'd learn this, Right.
How to ask those questions.
Right, exactly. And that's sort of, in other words, getting your hands, dirty with the scientific method, actually getting involved in the process of what question, when I ask this question, am I going to learn something new? Because there's a lot of ways of doing experiments where you won't really learn something new, and so figuring out the way to set up an experiment in the way, and such that the answer to the results of it will tell you something interesting and new is that's like the process of learning how to be a scientist. And there is an art to it that we don't really. I don't know. We're all we treat this as a very left brain type of thing, but there's definitely an art to science.
Yes.
There is an art to setting up an experiment and figuring out what is the way that, how do I set this up, in a way that it will give me an outcome that I'll learn something.
Oh, I think it takes a tremendous amount of creativity.
Yeah.
Otherwise, you're just asking a question that's been asked before.
Right. AI can do that.
But I do want to stress before we move on this point that you made, that I've listened to your other episodes, and I'm not sure it's been stated explicitly for the students listening. You are here to learn that process. We don't expect you to start grad school knowing everything, right?
Well, some people do, but they're wrong. So yeah, I mean, when the whole point of going to grad school is you're learning how to do this. Like some people, there are some go-getters who jump into grad school and they seem to know exactly what they're doing, but you just understand that's the whole point of you being there in grad school is you're learning how to be a scientist. You're learning how to ask those questions.
Yep.
And a lot of times it seems like your advisor just knows everything, just knows how to do things. But that's because they've spent like at least 10 years
right.
figuring out how, like, what all the blind roads will be and which path is most likely to lead to a reasonable answer.
Yep. I think grad school is that transition from interest and enthusiasm and a little bit of skill to knowing how to do this job, ideally. All right. So now you're an astrophysicist.
Yeah.
What do you love it? Do you hate it? What are some things?
Oh, I better love it. I've spent so much time. No, I do love it. I love it. It's I really, really love this job. I know you didn't even answer. I didn't let you finish the question, but I already know what it is. It's what sort of things do you like about this job? Actually, I wrote these questions because I was thinking about it. We were, a few years ago, we were interviewing for a new faculty position at Purdue, and and that was a question I realized is really important one to ask yourself at any stage of your career. What parts of your job do you like, and which parts of your job do you not like? And like pretty much every job, there are going to be some things you don't like, but it's good to pay attention to that and think about it, and it helps you understand whether or not you're in the right job.
Yeah.
Because, for example, a lot of my colleagues don't like teaching. A lot of my colleagues don't like dealing with students and stuff like that. But like that's most of your job now when you're a professor. And so if you don't like that, you should probably be doing something else. Right.
There are other ways of being a researcher.
But I love teaching. I think it's really fun. It's a lot of work because you have to do all this, prep, and you got to come up with, over an hour of material multiple times a week. That's a lot. But it's really fun and it's really rewarding. I think a lot of teachers probably feel this way, that it's one of the most rewarding things you can do. And it's funny though, because you're not hired to teach, as you're not really, when you're a professor at
it's what we're paid to do, but it's not what we're hired to do.
That's right. When you're a professor at a big institution, especially, they'll look for somebody who's a big name in research, who's done like some major research, and they won't care if you're a good teacher, which is why so many professors are not good teachers. But because that wasn't really what they spent their time focusing on. But I love it. I love teaching, and I love, actually, probably my favorite part is advising students.
Okay.
I like managing a team. Like, I love having lots of people working under me and like showing them like how I think, and trying to lead them to like figuring out how they want to approach problems, by showing them how I do it. And I don't know, I find that really fun, and I feel like it's kind of crazy, because growing up, I thought I was really good at math, and that was why I wanted to be a professor. But now that I'm a professor, I realize, no, I like being a professor because I like people, and I like working with people, and I like teaching them how to do this, do research.
Bringing back those leadership skills you got from your mom.
That's right. Yep. That's right.
So how many grad students do you have?
It depends on how you count, but I got about 5.
Okay.
That's
a lot for a theorist, by the way.
That's a lot for a theorist, but we haven't said that I'm a theorist yet.
Oh, sorry.
But I am a theorist, and usually a theorist will have 1 or 2 grad students, maybe. But I have 5, and they're all wonderful, and I love working with them.
Is there anything you don't like about your job?
I wasn't actually. Can I say more things I like?
Oh yes, of course. You can edit this however you want.
Well, yeah, it's true. I'm going to need to edit out a lot of the garbage I'm saying right now. But here's the other thing I really love. The top things are students related, teaching and advising. But the thing that have loved this whole time since I was in grad school, and even before, is I really love writing. I really love writing. I love writing papers. I love anything. I actually wrote a whole textbook, but I haven't tried publishing it yet, because I haven't gotten tenure yet, and I don't want to be spending all my time on a textbook. But I have written a textbook, and I really like that process. Like every single one of those processes is a process of communication, just in a different style. And I find technical writing really fun. And I find it really rewarding process to like get these concepts in my head onto a page. And I find that, anyway, I find nobody else has answered that. It's
something many of us struggle with. I want to add there, though, is there anything you're doing with your group and you're mentoring your students to encourage them to also like this process?
Well, I don't know how I can make them like the process of writing. But I do every once a week. I have a writing day where we all because that's a lot of it. Writer's block is a real thing, and especially when you have other tasks you're supposed to be doing as a researcher, you often put writing on the back burner.
Especially if you don't enjoy it.
Especially if you don't enjoy it. But even if you do enjoy it, you'll often put it off. And so I have one day a week where we make sure we show up, and even if you just write one sentence, just to get you going, you need to write a little, ideally for a writer, you should be writing a little bit every single day. And I know it's even when you really enjoy it, like I do, it often is really hard unless you force yourself to sit down every day and do a little bit of writing.
I really like this answer because I know so many of us, myself included, go into the science half of things because, I struggled with the humanities half of things. I'm not very good at writing, so I'll follow the numbers. But no, my job involves so much writing.
That's right. That's right.
And you have to be good at it, too. It's not, you have to be good at communicating your idea and telling this story.
You don't necessarily have to be, you don't necessarily have to have compelling prose like that draws people in. It's good if you do, but you do have to be able to, the thing that's in your head has to be able to get onto the page in a way that someone else will be able to understand
Communication skills,
And I really like doing that. I like that answer.
Now can I ask?
Go ahead and ask it.
Is there anything you don't like about your job?
I think you already know the answer to this question.
Probably.
Begging the government for money.
Oh.
That's like the annoying thing is a large portion of my job is trying to write research grants. And
I thought you liked writing.
I know, and that's the worst part about it is it takes something I love and like commercializes it, right? It turns into something where I'm forced to do in order to keep my group going, Mm-hmm. And so I have to, spend a huge amount of my time writing research grants and usually getting rejected for most of them.
The typical acceptance rate is what, 10 to 15% tops, so...
Yeah, it seems smaller than that to me, but but I did get the NSF AAG 2206299. I've now repeated. Every avid listeners of the podcast know that I mention that at the end of every episode because the NSF also likes it if you do outreach. So most of my grants that I've written have gotten big fat rejections, and you have to be able to deal with a lot of rejection because the acceptance rate is low, and so you'll have to expect you won't get most of the grants you apply to.
So you've been a professor for a few more years than I have. Do you ever get used to the rejections? Do they get easier at least?
Not really. I mean. They still suck. You still think you still have in your head, maybe I'll get every grant I applied to this year.
Because I thought it was such a good idea.
Right. I thought I read it so well, and then immediately reject it as soon as they see it. Nope, this is terrible. You still, no matter how many times I do it, I still think maybe I'll get every single grant I applied to this year. There's some devilish thought in the back of my head that thinks that gets control of me. And then when I get rejected, I'm like, oh, I thought I was gonna, I need, it's hard.
And the thing that drives me mad is from year to year, I could send in a very, very similar to the same proposal and get wildly different gratings and feedback on it.
Panel that reviews it, and so it's not you. But overall the process is probably about as good as it could be, but it's still not great.
Yep.
But yeah.
Yep. And to clarify, this money you need in order to pay those 5 students.
That's right. Yeah. They need to be paid. They need to get if they want to be on a research salary in my group, they need to be able to pay them.
Yep. Just wanted to be clear. This money doesn't go to us. This money goes to our ability to continue science.
I'm not writing all these grants so I can get richer. It's so that I can make sure and pay all my students.
Yep.
And if I were an experimentalist, I would typically want also lots of big experimental apparatus and stuff like that. But for me, it's almost all of the grant budget goes to personnel.
Okay. So I think that might be a good transition, actually, of into science.
All right.
If you're not, having a lab and needing equipment, what sort of science do you do? So if a grad student or a fellow scientist came up to you and asked, I'm going to rephrase this. I don't want to use your phrasing.
That's fine.
So how do you describe the type of scientist you are? What you do?
Well, the shortest answer I always give is I say, I'm Paul and I do hydro.
Okay. I think we might need a little more.
That's fine. I accept that. So generally what I work on is computational fluid dynamics. So what that means, the computational part is it's on the computer, and fluid dynamics. Now you might say fluid dynamics. How does that have to do with astrophysics? Well, of course, we talked with Yuan Li about how everything is a fluid out in space, but yeah, any gas, the sun is made of a gas, the planet's formed in a disk of gas. When they explode, they fling gas out into the universe. Basically most, I don't know if most, but a large portion of astrophysics problems are gas dynamics problems, which, fall under the broad category of fluid dynamics.
Okay, so gases are fluids in this
context. Gases are compressible fluids, right? So normally when the thing is, we use the word hydrodynamics to describe it, and you think that means water. And most people, when think of fluid dynamics, they would say that means, well, if you have heard of fluid dynamics, you would imagine that means water flowing through pipes or something like that. But we mean it more broadly broadly because gas, it's not the same as water because it's compressible, but otherwise it obeys very similar equations. So why do so computational fluid dynamics, to summarize then, that means that I'm putting that all together, is I take the equations of fluid dynamics, of compressible gas dynamics, and put them on the computer and basically evolve them to see how some astrophysical system will evolve. Whether it is, a star living its life, whether it's a star exploding, whether it's a gaseous disk accreting onto a black hole. There's just many, many different problems in gas dynamics in astrophysics. And so I end up working on a lot of them because I broadly work on computational fluid dynamics. And why do I get to work on everything? It's because mostly I started out working on the nuts and bolts part of how do you solve the equations of fluid dynamics on the computer. And so because I, work on developing algorithms and things like that, that means I end up getting to work on all kinds of different problems in astrophysics and apply those algorithms.
Okay, so you started out basically designing the methods for which the computer solves these problems, and now you get to apply them to whatever you want.
That's right. So when I was a grad student, my advisor was like, you should write this code. There was a researcher in Germany named Volker Springel who wrote this code called a repo, which used this. I'm not going to be able to describe it in words, but I will describe it in words, and then no one will understand it. But it's fine. They use the dynamic Voronoi tessellation, but basically a complicated mesh that moves to follow the fluid, and so rather than, the idea would be, in other words, the standard method of solving the fluid equations on the computer is you start with a grid of points or zones, and then you say the density at this point is this much, and the velocity at this point is this much, and the pressure at this point is this much, and then you let the thing evolve. But then this new technique was you actually allow those points to move and follow the fluid, and that way you're, ideally capturing things more precisely in the fluid, because you're, rather than passing the fluid from one zone to the next, you're having your sort of mesh follow the fluid. So you end up with this complicated mesh structure as it evolves. But anyway, so that's as broadly as detailed as I can get on a podcast. But the point is, this researcher in Germany had developed this technique, and my advisor said, "Hey, maybe you could do this too." Like this had just been developed by this seasoned, astrophysicist.
You were a second year grad student?
I was second or third year grad student, but he had spent years of his life developing this method, and he wrote a paper on it in something like 2011 or something, 2010, 2011, and my advisor was like, you could do this too. And that was the great thing. My advisor, Andrew McFadgen, is one of the great things about him is that he had such a high opinion of me. There was no task that was too crazy for me to do. And that ended up really working very well, because he would just be like, hey, maybe you could develop a method to follow the fluid using this moving mesh thing. And I looked at it, looked insanely complicated, but I also looked really cool. It looked like a really beautiful thing to do. And so I got hooked, and I wanted to try to figure out if I could do it. And eventually it took a while, but I was able to do it. And we managed to actually get a paper out on the method 1 year later. So we were, he was totally right to give me that task, even though it seemed like a totally insane task to give a grad student.
And that meant you could then use that method.
And then I had the code, so now I have my own code, and I can use it to apply it to whatever problems I wanted to, whatever astrophysical research problems I wanted. And so that's what I did for from then on, is just applied it to all kinds of different problems. Do
you have a favorite type of problem?
I don't.
Sorry, you hate favorite questions.
I don't have a favorite.
That's why you do everything.
That's right. I can't choose between my babies, but I do. Probably the first thing that I worked on that got sort of noticed was doing planet formation and how the planets formed in a gaseous disk, and how they affect the disk as they're forming in that disk. So when the planets form, it's first a disk of gas and dust, and at first there's no planets at all, just a bunch of dust, and then the dust just clumps together, and then those bigger grains clump into bigger grains, and then they get to bigger and bigger, and eventually they're planet size, and their self-gravity starts to clump them together. And they start to be large enough that they interact with the disk. And there are many examples where we've started to see we have observations of protoplanetary disks where we see the planets have carved out gaps in their disk, and so there's basically, it's like you see this nice disk, but then there's this like hole, there's like an annulus, there's all like a cleared out gap, and in many cases, some of those cases, we think it's caused by a planet being in the disk. Cool. And so we're actually not only is this a way of like discovering planets, but it's a way of watching the process of planet formation in action.
Okay, so these experiments that you're running on your computer, these models, are helping us to inform then what we see when we look out at these protoplanetary disks and inform what those gaps mean?
Yeah, so for example, so if you look at a particular disk, you might say there's a gap in that disk. Is it a planet? So the first thing you can ask is it consistent with there being a planet there? But if there is a planet there, then, how massive is the planet? Can you figure that out based on the shape of the gap? Or how, what else can you learn about the disk maybe, from the gap? And so that's teaching you about the environment that the planet formed in, how quickly planets can assemble to certain masses. It's teaching you all about like the very early stages of planet formation, which teaches us about where we came from, how our solar system formed. And
this is very new science, right? When were the first protoplanetary disks resolved at such a way where we could see those?
Who you talk to.
Yes.
But the really dramatic images that have been seen by ALMA, I think that was 2014 or 2015.
Okay.
When we first started to see the big image that sort of started, that's 10 years ago, was HL Tau. And when we saw that, we could actually see that there were, in that case, it may not be due to a planet, but we can see that there are these ring structures in the gap in the disk. And when we saw that, it was like this big game-changing moment where we said we can actually resolve these disks well enough. We can see there's stuff going on in them, and we can try to make detailed models of these newly forming solar systems. And so that's HL Tau, and that was 10 years ago, and that was this ALMA.
And that was right around when you were finishing your PhD?
I was right around when I was finishing my PhD, because I got my PhD in 2014. So that's how I remembered when it came out. But yeah, it was. But so that, I would say that was the big shift, is being able to actually not just like, before that we could resolve some stuff where you'd see like a fuzzy blob and you're like, that's a disk, you can see how big, how you can measure the size of the disk and that sort of thing. But now it's much more than that. You can actually see the solar system, you can see details in the structure of the disk and how the solar system is being formed. This
is part of what I love about our job, is that, we think of these things for such a long time, and then suddenly we make breakthroughs where we can actually go and check.
Right. Yeah. Well, for me, I don't have as much of that, but I mostly kind of most of my work has been kind of trying to develop things that help us infer data from existing observations. I haven't done a lot. I can't think of a good example where I've done like a prediction that then comes true, but that's okay. Not everybody can do that. I can still be useful in basically providing a theoretical backbone to help us infer information about these systems from looking at them. Okay.
So, as a computational astrophysicist, a computational fluid dynamicist, what does your day-to-day look like?
So my day-to-day, well, for me as a professor, my day-to-day, a lot of it looks like, just meeting with my students and seeing how they're doing. But I would say as a researcher, when you're working on these projects, a lot of the day-to-day involves, debugging your code, figuring out why your code isn't working, That's most of it.
Yep.
It's all well and good. You've written a beautiful code, and then you apply it to a new problem, and then it doesn't work, and you have to figure out why. So that's most of your time, and you have to be. I mean, pretty much every branch of science has this aspect to it. Research, right? If it weren't hard, then someone else would have already done it by now. So there's always going to be, like, whenever you try a new problem, something about it is not going to work at first. So your code's going to crash. You're going to have some, there's some issues, like, not that there's like a bug in your code, but it's just a hard problem that the code has trouble solving. And so that's a lot of it is figuring out, okay, what's wrong with it? How do I set it up in a way that it won't crash? How do I set it up? What is causing it? Doing a lot of figuring out troubleshooting, basically. So and so that's a lot of the day-to-day, is really just figuring out why isn't it working, and then eventually it does work, and then you have to then you'll run it a bunch of different test cases and try to figure out what are the laws that the system obeys. And for example, if you want to know how deep a gap a planet opens in a disk, you'll try a bunch of different planet masses and see what is the rule that is following. Like, it gets deeper the heavier the planet is, and so because it's carving out a deeper gap because its gravitational influence is stronger. And then what is that law, and does that obey the rules that other people think that it should obey, and that sort of thing. And so setting up the problem on your computer so you'll really learn that, you'll really learn what those laws are. And so that's a lot of it is debugging and figuring out how to set up the problem, and what sort of parameter space you're trying to move around in.
Cool. Yeah,
I don't just work on planets, too.
Okay,
I was using the planets as an example.
Yes, it's a very coherent example. I was about to ask, what do you think your most impactful contribution has been?
I don't know.
But instead, you can talk to us about what other things you enjoy.
Well, one thing I really enjoyed, I talked with my student, Shoam Mandal, who got his PhD and now is at University of Virginia. And he worked on supernova remnants. And so he wrote his own code. Passing the baton on now. He wrote his own code to do this, and you're like, why does everybody have to write their own code? Like, why can't everybody just use one code, right? Well, each problem you can tailor a code to do that problem better. So the problem he worked on was supernova remnants, which is long after a star has exploded, long after a supernova. That stuff is still flying out there for hundreds of years, thousands of years. We can still see it for up to maybe 1,000 or so years. And then we can, by that time, it's expanded to be so large that we can actually resolve an image of it, and they look beautiful. So if you Google, like, Tycho supernova remnant or something like that, you'll get this beautiful cauliflower-like image.
Taken with Chandra, probably.
Possibly. Well, taken with a number of instruments. Not yet with JWST, but with Hubble and Chandra. And
funding panels, if you're listening.
Yeah, that's right. You should definitely observe it with JWST, the Tycho supernova remnant. But anyway, the point is, what can you learn from that structure? And so, so that was another thing that Shoam did, was he developed his own code to do this, where he had a code that expanded to follow the super, because it has to expand over and over, like by factors of like 10,000, right? So if you just have a single grid, you'll need a really, really high resolution in order to resolve it when it's very small, and when it expands up by a factor of 10,000.
So let's take a step back and make sure we understand why there. So if you're breaking up, I don't know if I can do this better. Can you?
Yeah, my job isn't so easy, is it?
Yeah.
Your guest says some weird, complicated thing, and then you have to try to explain it in a way that people understand.
If you imagine it, and let's go with U.S. units here. If I have a foot,
okay,
and I want to split that up into 12 equal segments, what do I get?
You get inches,
right? But if I want to take 12 feet and break it up into 12 equal segments, it's a foot. So you don't have the same resolution and the same number of grid cells. You either need to choose many grid cells.
In other words, if my code wanted to resolve 12 feet versus wanting to resolve 1 foot, then
we can cut this out.
I'm not sure we've explained it any better, but the idea is you have some code, some computational domain, and if that, if the star starts at a very small size, and it explodes, only the size of a star, and then expands to 10,000 or more times that size.
Right.
Then if you have one grid that tries to resolve all of that, you need a way too high a resolution to capture.
And resolution here just means the number of grid cells.
You need a lot of grid cells to resolve that, and we just don't have that kind of computational power anywhere on Earth. And so Shoham developed his own code that will start where the grid starts very small, and then it expands out to follow the gas dynamics, and so that you can cover every order of magnitude of expansion and resolve every order of magnitude just as well. So it's a very powerful technique that he developed. But anyway, that's another, I don't know, you asked me for my most impactful contribution. I thought about most recent thing that I thought was really cool.
I mean, Supernova Remnants has been fun for both of us too, because it's the first topic we allowed ourselves to work on together.
That's right. Yeah. We actually got to collaborate on, that's true, that's another reason I liked it. We were able to collaborate on a Supernova Remnant project together. And so, it's fun to sort of think about the gas dynamics of things like that, especially that you can actually see resolve with a telescope and say what's, try to ask questions about what's going on. I don't know if that answers the question well, but it's okay. I'm just a bad guest. That's fine.
Most impactful versus most interested in right now. Who can tell?
I don't have a most impactful.
I always hate the most impactful question.
I will say,
I hope it's something I do in the future.
Well, that's true. Yeah, that would be nice. I will say one thing that I did recently that I think is a big deal was I did this big, what we call code comparison. So this was, I got together, at least a dozen different researchers, all of us working on the same problem in astrophysics, which is how does a binary system interact with a gaseous disk?
But all using different codes to do this?
All using different codes. And we're all competitors, right? We all hate each other. No, we don't hate each other, but we're all competing, and we all think each other's wrong about stuff, right? Yep. And so, I mean, that's an oversimplification, but a lot of people, think that each other is doing things wrong, or that their codes aren't accurate or whatever. And so, one of the things I did was I organized this big comparison where, a bunch of us would get together and do exactly the same problem. We set up all of our codes, do exactly the same problem, and see if we all got the same answer, and if it looked first of all, if we could just agree on the answer to this problem with how a binary interacts with a disk.
And that task is much harder to accomplish than it sounds, of actually solving the same problem using such different methods.
That's right. So it's a lot of work just setting up the problem so that all codes were sort of, first of all, fairly compared. But
was it hard coming up with a problem in the first place?
I think that I think that it's usually hard. I think that we did a good job, getting together and agreeing on a problem pretty early. But that is normally something that's easy to screw up. Is to pick a problem that is too hard for all codes to do at the same time.
Right.
Anyway, the point is I really like that because first of all, it's getting everyone in the community together and saying maybe we don't disagree with each other about sort of fundamental things about how we think the system behaves, but we all ultimately want to know what happens, right? We all ultimately want to know what the answers to these questions we have are. So can we all get together and just try to understand that? And you do need a bit of trust there that we're not trying to screw each other over or try to say our code's better than yours or that sort of thing, but anyway, that was a big project that I was really happy to lead.
Yeah, it sounds, again, like an example of those people skills are very necessary in order to accomplish something like that.
I've seen things like this where they just crumble because, people just get too snarky with each other and too competitive. So it's very important to be, to develop an atmosphere of trust. So people skills are really useful for that.
How did that idea get started?
How did it get started? Well, we were at this program at the KITP, Kavli Institute for Theoretical Physics in Santa Barbara. So there's a program on basically the whole, it's a scientific program on binary disk interactions, which seems like a really specific thing to have a whole bunch of researchers get together and talk about. But it was like it was for several months where people would just get together and meet and talk and come up with research project ideas. But it was just on how a binary interacts with a disk, which is actually a problem that persists throughout a lot of astrophysics. I didn't say whether it was a binary star system. It could be a binary star system when a solar system is first forming, but with a binary, like Tatooine, right? That when that solar system first formed, you had two stars at the center and a disk around it. And how did that change how the solar system formed? So that's one reason we care about how binary disk interactions work. It also affects, how what binary star populations should eventually look like, because how that disk interacted with the binary would affect it. But it also is important in a totally different field, which is black hole binaries. We now have the ability in multiple ways to observe gravitational waves from black hole binaries, and a lot of those systems have interacted with the disk, and we want to know if the disk imparts any physics onto like the signal that we see from these black holes. We know that black holes accrete lots of gas, and if there's a binary, it should also accrete gas in a disk. And so that binary disk interactions, now those systems we don't get to see. We don't get to look at them like we do with ALMA, where we get to look at a binary interacting with a disk and see what it does. But they're very important in understanding sort of the nature of our reality, because they're telling us about black holes and about gravitational waves and how black holes form throughout the universe. So these are deep fundamental questions about the universe that we're learning, but we can't look at them in the same way we just look at a binary star system,
because they're not releasing photons.
Because we don't, exactly, they're black. They don't. That's one of the basic things about them. They're
Are these systems we can look at with gravitational wave detectors?
Yes. The ones that I'd be thinking of are supermassive black hole binaries. We can't see with there's LIGO, the gravitational wave observatory that we have in the U.S. One in there's two buildings, one in Hanford, Washington, one in Livingston, Louisiana, that observe gravitational waves from black holes that are around like 10 to 30 times the mass of the sun, something like that. So pretty massive, but not nearly as massive as these supermassive black hole binaries. That LIGO cannot detect these. These are like 1 million to 1 billion times the mass of the sun. Those can be detected by these things called pulsar timing arrays. I don't know if I want to get into how pulsar timing arrays work, but it's a new method that we've just, in the past few years, been able to get a signal from, where we see gravitational waves, which are, I will say what gravitational waves are. They're ripples in the fabric of space-time. There are various ways of detecting those ripples in the fabric of space-time, but they're very weak, so you have to have very sensitive techniques for detecting them. So we're able to observe those from supermassive black hole binaries now, and we want to know if that affects if accretion from a gaseous disk can be sort of pulled out of that signal, if we can learn anything from that.
Yeah, this is the question everybody loves. Are you ready for it?
Yeah, I know it.
In your opinion, why should we care about astrophysics?
Yeah, that's a good one.
Well, you wrote it.
I wrote it, sorry. I asked this question of every guest. Actually, you only had to go really quickly, so I didn't get to ask her. But everyone else, I asked this question, this is actually I've gotten the most variety of answers from, and I still don't know the answer to it.
Oh, so that's why you ask it.
That's the one I genuinely want to know the answer to, because I know that I love it and I love studying it, and I know that the community really wants to know this. Like. But it's funny because other fields of physics, for example, like condensed matter physics, even particle physics, there is a pretense that we're going to use this to like develop something for industry that will be used in some way to hopefully benefit a society.
Sometimes.
In many cases do benefit society. You know, like a lot of developing new materials that can help out society. That there's like new new superconducting materials or new smaller microchips and things like that. They're definite tangible benefits to every one of us. Astrophysics does not have that. It doesn't have a direct, immediate impact that like you can find in a practical sense. It's much more. It's much harder to give a good answer to that question because there's most other fields of physics they can and of course we try to, when we write grant proposals, we try to say how it will benefit society, but ultimately it benefits society because people want to know these answers. These are some of the deepest questions you can ask in the world, and we can actually hope to build concrete answers to these questions. And it's kind of crazy, like it's amazing because it's so not practical. Like there is no reason that anyone on this planet needs to know what black holes are. But like, how can we go through our lives knowing that they exist, but not knowing, everything about them? Like we want to, like,
right.
They're fascinating. Like
there's a supermassive black hole at the center of every large galaxy.
Right. And we don't,
including ours.
We don't really that well understand why that is. I mean, in some sense, but like the details of it we don't really get. And so like there are like lots of deep questions that we as humanity only partially knows the answer to. And so like we can actually, we have the hope with modern technology. We have the hope of actually answering these types of questions. But then, does it actually benefit anybody on Earth? Well, it depends on who you ask, right? It's not like curing cancer, right? But it benefits us in a different way. It helps us learn who we are, like what this universe is that we live in. Where did we come from? Whether you mean where did our solar system come from or where did the universe itself come from? Like there are really like what you would normally categorize as philosophical questions, but we're turning them into scientific questions.
Yes.
And so to me that's a big deal, but it's not the same thing as developing a better microchip, right? You don't have the same kind of impact on everybody's lives that you would if you were doing a different field of physics.
Yep. I would like to say, and you can get rid of this later if you want, but I would like to say that doesn't really apply to the instrumentation side of astrophysics, just, the thinking side. I'm pretty sure we invented the CCD, for example.
Well, right, but that's fine. There's tons of, we invented satellites,
yes.
Right? We invented, GPS technology, cell phones, that's all thanks to astrophysics, but it's things we kind of happen to discover along the way, like because we were interested in this deeper question, right? So of course you can always point to things that astrophysics has done for society, but those weren't things that's not why we were doing it.
Yeah, that's a good point.
So anyway, that's my answer. That's, at least after a year of asking that question, that's now my answer.
I feel like we should come back every year and maybe not have you do the anniversary episode every year, but every year how has your thoughts about this specific question evolved?
That's my current answer to it. But if you're a funding agency, I can come up with lots of practical uses and I'll give you them. But that's my real answer.
All right. So what's next for you? What's on the horizon? What's your next big task to tackle?
Let's see. I'm planning on doing another year of the podcast at least.
Excellent.
That's not that's not really what that question was intended to ask. But I don't know. We have a lot of this thing is I work on so many different things in my group that there's no end to the different types of things I'm interested in. This supernova remnants are finally really exciting with JWST. I mean, they were exciting before, but I think JWST is allowing us to look at them in new ways, and we're starting to develop theories about how they work that we can actually quantitatively say what happened to cause the structure to look the way it does. I think that's really cool. there's no end to like all the laundry list of things that I'm interested in doing. I didn't even talk about half of the things we do in my research group, and so I'm not going to get started on that now. But but we have a lot of stuff that we do that I'm really excited about.
Well, thank you so much, Dr. Duffell, for joining us. I had a lot of fun doing this. I was nervous about it when we pitched the idea, but I actually did have a lot of fun doing this. So thanks for letting me host, and I hope we'll see you again sometime.
No chance of it. I'm done. All right.
Happy New Year, everyone.
Thank you for hosting.
Thanks for asking me.
Well, I can't believe it's been a whole year already. I look forward to another year's worth of podcasts so long as I can continue to find astrophysicists willing to share their story with me. It's funny, I've known some of these colleagues for years, but it's amazing how much you can learn about someone just by asking them. Thank you so much to Professor Polin for hosting the podcast this month, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206299. If you want to connect more, or if you have astronomy or astrophysics questions, follow me on Blue Sky at paulduffel.bsky.social. All music on the Astrophysics Podcast was written and recorded by Britton Ashford. You can find it on her album Trotter. All songs are used with permission from the artist and producer. Look up Britton Ashford if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffell, Professor of Physics and Astronomy at Purdue University.